Hello, and welcome to Homework Help for Math 2. Today we're going to be looking at Unit 1, Lesson 1, Quadratic Functions, something to talk about. As a reminder, each problem that we're going to go over in this video has been time-stamped, so feel free to navigate to a specific problem if that's what you're looking for. We're going to try wherever possible to start with a hint to get you started. If that is enough for you to finish the problem, I would encourage you to actually pause the video and try to finish the problem on your own. However, in this video, we are going to be going over the solution for each problem. But again, you are encouraged to really only use as much as you can to sort of get started on a problem if you are stuck. So let's go ahead and get started. First set of problems are in the ready section, and we are being asked to rewrite the following expressions by applying the distributive property. So, number one, what we want to do is we want to take this 3 and we want to distribute it to each term inside the binomial, and we're going to do that via multiplication. So, 3 times 2x, you simply multiply your coefficients and we get 6x. And then 3 times 7 is 21, giving us a final answer of 6x plus 21. For number 2, we are again going to take our monomial, our sort of leading coefficient, and we're going to distribute it to both terms of this binomial. Notice that our monomial this time is a negative, so please don't forget about that negative in front of the 12. But again, we're going to be distributing via multiplication. So, negative 12 times 5x is negative 60x, and then negative 12 times negative 4 is positive 48. Giving us a final answer of negative 60x plus 48. For number 3, we are again going to distribute our monomial to both terms. This time our monomial has a variable in it of a, so we just want to make sure that we include that in our multiplication. So 5a times negative 3a is negative 15a squared. It's negative because we have a positive times a negative. The 15 comes from the 5 times the 3, and the a squared is a times a. And then our second term is 5a plus 13, which is 65a. So our final answer is negative 15a squared plus 65a. For number 4, very similar to number 3, we want to distribute our leading coefficient, our monomial, to each term inside the binomial. We're going to do that via multiplication. So 9x times 6x is 54x squared. Again, 9 times 6 is 54, and x times x is x squared. And then 9x times negative 2 is minus 18x. So our final answer for number 4 is 54x squared minus 18x. Last problem in this section that we're going to do, number 5, very similar to the first 4, except our monomial happens to have a fraction in it. So if you're not that comfortable with fractions, you could use a calculator here. However, I would encourage you to sort of think about what is happening in this problem. When we take 2x over 3 and multiply by 12x, we're going to take 2/3 and we're going to multiply by 12. Well, another word for multiplication is of. So what you can really do is you can think of this as 2/3 of 12. what is 2/3 of 12? Well, 1/3 is 4, and so 2/3 would be 8. So we end up getting 8, and then of course x times x is x squared. Again, if that multiplication kind of throws you for a loop, you could go to your calculator and type in 2 divided by 3 times 12, and you'll get 8. However, if you can sort of think about what's happening here with the fraction, it will make your life a little bit easier. So 2/3 of 12 is 8. And then 2x over 3 times 18, again, we're looking for what is 2/3 of 18? Well, 1/3 is 6, and so therefore 2/3 is going to be 12, and then just a single x. And again, if getting that 12 is a little tricky for you, you could go to your calculator and simply type in 2 divided by 3 times 18, and you'll get the same 12 that we just got here. So our final answer is 8x squared plus 12x. Our next set of questions are in the set section. And the directions for number 8 say create standard mathematical representations, so a table, graph, or equations, that relate the figure number to the number of squares for the sequence of figures. Find the number of squares for figure 4. Okay. So we have figure 1, figure 2, figure 3. They're all rectangles. They're comprised of a bunch of smaller squares. We have a table here describing figure number 1, 2, 3, and 4. Notice that 4 is not shown. We're being asked to find the number of squares. We have a space for graph, and then we have space to write equations. And as a little preview for the equations section, I'm going to go ahead and write this right now. For the equations, we are going to need both an explicit equation as well as a recursive equation. So I'm just going to get ready to do that in a little bit. But before we get there, let's just go ahead and fill in the table. So for figure 1, it's easy enough to count them up, 1, 2, 3. So we have 3 squares. For figure 2, you could count them. You could also notice that this is a rectangle where my height is 2 squares, and my, we'll call it width, is 5 squares. And the area of a rectangle, which is also the number of square units in that rectangle, is simply these two dimensions multiplied. So 5 times 2 does in fact give us 10. And if you count them up, you'll get the same 10 that we just got. Looking at figure 1, 1 times 3, of course, is also 3. This same strategy should work for figure 3. If you go ahead and count them up, you'll get 21. But even easier than that, in my opinion, is the height is 3, the width is 7, the area represents the number of squares, and 7 times 3 is in fact 21. Now, the question didn't ask us to sketch, so this isn't strictly necessary, but it might be helpful to sort of visualize this. I'm not going to bother with all the squares sort of in between them. However, hopefully you guys are already starting to notice some patterns here in terms of the dimensions of these rectangles. The height goes from 1 to 2 to 3. I think it's pretty reasonable to assume that figure 4 is going to have a height of 4. And again, this is figure 4. So 1, 2, 3, 4, relatively straightforward. The width is just a little bit more complicated, but nothing too crazy. We start with 3, then we go to 5, then we go to 7. And there does seem to be a pretty clear pattern here where they seem to be increasing by 2. So 3, 5, 7. Our next width really should be 9. And it is 9. So counting up the squares would be starting to get a little tedious, but luckily we can simply do 9 times 4, and we in fact get 36. So figure number 4 should have 36 squares in it. Now, in order to graph this, we can actually go ahead and graph this right now. We don't really need to do anything else in order to do the graph, so we might as well go ahead and finish that. So I would encourage you, as you're graphing, to use a straight edge. I'm just going to do this freehand, but if I were doing this on paper, I would be using a ruler or some other thing as a straight edge for those lines. It's a little bit tricky on the rig here, so we're just going to leave it like that for now. So I've got an x-axis and a y-axis. My x-axis is going to represent the figure number, right? So figure number 1, number 2, number 3, things like that. And my y-axis is going to be the number of squares. So my x-axis, which is also my independent variable, is the figure number, and my y-axis, my vertical axis, which is my dependent variable, is the number of squares. Now we have to come up with a scale for this graph. Well, the scale for the x-axis is relatively straightforward because I only need to fit 1, 2, 3, 4. So I'll make it, every, say, 2 boxes, just to give us a little bit of space. So this will be 1, this will be 2, this will be 3, this will be 4. We got plenty of space to continue if we wanted to. Now the vertical scale is a little bit more complicated because we need to be able to fit at least 36 going vertically, and hopefully you can tell just by looking at this that there are not 36 boxes in the vertical direction. So we're going to have to come up with some sort of scale that makes sense. And there isn't necessarily one correct answer here. I am going to choose to go every 2 boxes is going to represent 5 squares. So what that means is my first hash mark here, 2 boxes up, is going to be 5. Then another 2 is going to be 10. Another 2 is going to be 15. Another 2 is 20. Another 2 is 25. Another 2 is 30. Another 2 is 35. And we can see that we're going to be able to fit 36 in this graph. So now we just want to plot our points. Go ahead and use a larger dot here. So for figure number 1, we want 3 squares, which is right about there. For figure 2, we want 10 squares, which is right there. For figure 3, we want 21, right about there. And for figure 4, we want 36, right about there. And that is our graph. All right. So we've done most of this problem now. We filled out our table. We've graphed it. We figured out how many are in figure number 4, which is 36. Then we just need to come up with the equations. Now, in my opinion, this is probably the more challenging part of this question, but certainly not beyond our capabilities. We are using function notation in this context, so both the explicit and recursive equations are going to start with f, sorry, f of n, f of n. So with both of these, our function name is f and our input is n. With an explicit equation, our explicit equation is going to be in terms of n. So what we want to do is we want to come up with some way of determining the number of squares for any figure, figure 5, figure 12, figure 100. And we want to be able to do that by simply plugging in that number, 5, 12, 100, n in this case. Well, remember that when we were looking at the figures themselves, we noticed that we can think of these in terms of area. So for figure 1, notice that our height, which is 1, is itself the figure number, right? Figure 1, in this case, right, is n. So this is figure n, figure 1. And that 1 is my height. So my height here is, in fact, n. And then for my width, well, it's a little bit more complicated. So actually, we're going to come back to that in just a second. Notice that for figure 2, now that's my n, and my height is 2, which means my height is still n. For figure 3, that's n, and my height is 3, which means my height is still n. And of course, for figure 4, that's my new n, and my height is 4, which means my height is n. So notice that for every single rectangle here, my height is the figure number. 1, 2, 3, 4, n, 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 figure 1, figure 2, figure 3, figure 4. So the height is relatively straightforward. Now, notice that my width is increasing by 2. So what that really tells me is that I'm going to need, in all of these, move up just a little tiny bit right there, okay. So if I want to express my width in terms of n, I'm because they're increasing by 2 every single time, 3 plus 2 is 5, plus 2 is 7, plus 2 is 9, I'm going to have to kind of start with a 2n. And I know that if I want to express my width, it's going to have this 2n in it, because every single time I increase the figure number, the width increases by not 1, but it increases by 2. So that's where that 2n comes from. Now, if I look at figure 1, and I look at 2n, well, if n is 1, then 2n is just 2, but I want 3. So what I really need to do is I need to take that 2n, and I need to add 1 more to that. And hopefully you guys can see that if I let n be 1 and I plug it into this expression, well, 2 times 1 is 2, plus 1 is 3, which is exactly what I want. For figure 2, again, notice that if I let n equal 2, I get 2 times 2, which is 4, but I need to add 1 more to get the 5 that I want. For figure 3, if I let n equal 3, I've got 2 times 3, which is 6, but I have to add 1 more, giving me 7. And for figure 4, if I let n equal 4, 2n plus 1 is 8, which means I need to add 1 more to get the 9. So again, there's a pretty clear pattern here. Every single rectangle, the dimensions are n times 2n plus 1 for figure n. So if I want figure 10, then my height is going to be 10, and my width is going to be 2 times 10 plus 1, which is 21. So this pattern will hold. So for my explicit formula, what I can do is I can say, all right, well, the number of squares every single time is going to be my height, which is n, times my width, which we just said is 2n plus 1. So that's my formula, n times 2n plus 1. If you want to distribute, you get 2n squared plus n. And really, I think that both of these would be acceptable. So whether you want to distribute or not, for now, we'll just say both are okay. That might change in a subsequent lesson. But my explicit formula is going to be f of n equals n times 2n plus 1, which is the same thing as 2n squared plus n. And again, the way that we got that is by sort of looking at the pattern here that exists with the dimensions of the rectangle and figuring out, all right, well, how do I get my area? And I multiply them together, and we're good to go. Last part of this question is, what is a recursive formula for the same pattern that we're noticing? Now, with a recursive formula does not refer to specifically to n, it refers to my previous term. So if I'm talking about f of n, my previous term is going to be f of n minus 1. So for example, if I'm looking at, like, let's say figure 3, I want to relate figure 3 to figure 2. So I'm looking at the one behind it. So I'm saying, all right, my new figure, f of n, is my old figure, f of n minus 1, and then I have to modify that in some way. Now, if you haven't done this already, this is going to be a good time to go back to my table and to look at our first and second differences. And what I mean by that is my first difference is going to be, what do I need to do to 3 to get 10? Well, I need to add 7. Okay. If I want to look at going from 10 to 21, my difference is 11. And if I want to go from 21 to 36, I need to add 15. So those numbers, 7, 11, 15, are what's known as the first difference. I also want to look at the second difference. Now, the second difference is essentially the difference of the difference. So now I'm going to do the same thing, but I'm going to look at my new numbers. So again, what do I need to do to 7 to get 11? Well, I need to add 4. And what do I need to do to 11 to get 15? Well, I need to add 4. As we saw in the lesson, this pattern indicates that we have a quadratic relationship. We have a quadratic function. And what I mean by that is that our first differences are a linear pattern. They're increasing by the same amount, 7, 11, 15. That is a linear pattern. And then our second difference is a constant. Our second difference is just 4. 4, 4, 4, 4, 4, 4, 4. That pattern tells us that we have a quadratic function, and it's a key understanding in this lesson. So please make sure that you're pretty solid on that. Now, in order to get my recursive function, the way that we're going to do that is we're going to say f of n equals f of n minus 1, and we are going to add our second difference, which in this case was 4, and we're going to multiply that by n. So f of n equals 4n minus 1 plus 4n. And then we also need some constant, right? There needs to be a little piece sort of like right there that we're missing. And there's a number of different ways that we can get this. In my opinion, I think the easiest way to do this is to actually look at my first two figures and sort of figure out, all right, how would we need to modify this equation in order to finish out this recursive formula? So if I want figure 2, if I want f of n, we know, I'm going to do a little box over here of some side work. So I know that figure 2 has 10 squares in it. Okay, so that's f of 2. And my recursive formula says, take my previous figure, which is figure 1, which had 3 squares in it. I already know that I need to take my second difference, which was 4, and I need to multiply by n. Now remember, we're talking about figure 2 here. So therefore, in this situation, n is 2. And I need to do 4 times 2. And then we're missing some other number here. I don't know what that is. That's what's going to go in this sort of highlighted area for the recursive formula. Well, I have an equation here that I can solve without too much difficulty. I've got 10 equals 3 plus 8 plus d. So 10 equals 11 plus d. Subtract 11, subtract 11. And I end up getting that negative 1 equals d. And so what that means is, and I'll go ahead and erase that highlight right here, it means that the final part of my recursive formula is going to have a minus 1 at the end. Not the easiest problem in the world, and it would actually be a little surprising if people were able to get this on their first try. But don't worry, we're going to have plenty of time to practice this over the next couple of weeks. But again, in order to get the recursive formula, we refer to the previous figure, f of n minus 1. We then add n times my second difference, which in this case was 4. And then we need to do just a little bit of algebra in order to figure out what is the sort of last piece of my recursive formula. Turns out it's negative 1. There are other ways of finding the negative 1. So if you want to look at an alternative way, I say come to office hours and we can discuss. Moving on to number 9. We've kind of already answered some of these questions. So we've done most of the work for 9 and 10. We just now need to articulate it. So number 9 says, how does the rate of change for the relationship in problem 8 show up in the table? Well, we've talked about differences here, so I would say we should focus on that. What I would say is the first difference in the table differences, sorry, are linear. And the second differences are constant. Specifically, it's 4. This means the relationship is quadratic. We have a quadratic relationship, again, because the first differences are linear, 7, 11, 15, and the second differences are constant, 4, 4, 4. That tells us that we have a quadratic relationship. For number 10, how do the terms in the equations connect with the diagrams provided? So the way that you phrase this might be different, so I'm just going to sort of phrase it the way that I would think about it. I would say that if we're talking about the explicit formula, that's probably the easier one to think about. If I look at, say, f of n is n times 2n plus 1, well, as we talked about, n is the height, and 2n plus 1 is the width, or length, however you want to say that. And f of n is the area. If you want to look at the distributed version, 2n squared plus n, well, n squared is a large square. And what I mean by that is, if we go up to my figures here, let's look at figure 3. You have one square, that's n by n. You have another square, that's also n by n. And then you have a column that's only one across, but is still n high. So n squared is a large square. And there's 2 of them. and n is an additional column. Now, if your answer does not match this exactly, that is perfectly fine. I would encourage you to try to connect these equations to these figures and try to make them not just a bunch of random math symbols, but sort of like why is this work this way? And if you're not used to thinking this way, you'll get there. Just give it some time. The next set of questions are in the Go section, and our directions say identify the rate of change in each of these contexts or representations of linear functions. So this section is all about linear relationships, linear functions. So we're going to sort of table quadratics just temporarily. We're going to focus exclusively on linear functions. And we're looking for the rate of change. Well, rate of change is another name for slope. So for number 11, basically just asking, what's the slope of this line? Another concept for slope, another way to represent it, is rise over run. So if I choose that point right there and that point right there, we are looking for my rise, which is going to be 1, 2, 3, 4, over my run, which is 1. 4 over 1 is 4. That is my rate of change. Next question is 13. Skip down to this one. So for 13, we are again given a linear function, a linear relationship, just like we did with 11, but instead of giving it in a graphical form, we are given a table form. But it's still a linear function. This is still structurally the same thing that we just looked at. It's just being presented differently. So here we have x values increasing by 1, 25, 26, 27, 28. And each time we've got 65, 68, 71, 74. Well, each time they're going up by 3. The rate of change, m, my slope, is essentially saying, well, each time I increase my input, what happens to my output? And each time it's 3, so my rate of change is 3. Final answer. Next question is 14. And again, we are given a linear function, a linear relationship. This time, we are given our information in a recursive formula. So we're told that our f of 0, our first term, is 7. And then f of n plus 1, so our next term, says we'll take our previous term and add 5 to it. If you wanted to do a real quick table, you could. This part is not strictly necessary, but if you were to make a table, well, f of 0 is 7. My next term is my previous term plus 5, so term 1 is going to be 7 plus 5, which is 12. My second term is going to be the previous term, which is 12, plus 5, which is 17, and so on and so forth. And you should pretty quickly be able to see that my rate of change is simply 5, which is this number right here. So my rate of change is 5. Next question is 16. For 16, they are telling us that we want the slope of line AB, and again, as we've mentioned, slope is a rate of change, and we're given 2 points. So in order to find my slope this time, we need to use we need to use our slope formula. Well, we don't have to use our slope formula, but that's what we're going to use. So our slope formula, as a reminder, is y2 minus y. I'll go ahead and write it. y2 minus y1 over x2 minus x1. The order here doesn't really matter as long as you're consistent. You can either go from A to B, or you can go from B to A. Again, you just need to pick one and then be consistent with both x and y. I'll just go from A to B. So that means that y2 is going to be my second y term, which is negative 16. I'll go ahead and label them as well. So right now, this is x1. This is y1. And then this is x2, and this is y2. So y2, like I said, is negative 16. y1 is 12. We are subtracting that. x2 is negative 11. And then x1 is negative 3, but notice that I'm subtracting it. So when I subtract a negative 3, what I'm really doing is I'm adding 3. Okay. I can go ahead and simplify this. Negative 16 minus 12 is negative 28. And negative 11 plus 3 is negative 8. Technically, that's our answer. We have a negative over a negative, so the negatives go away. Also, if you want to reduce this fraction, both 28 and 28 and 8 have a common factor of 4, which means this does reduce to 7 over 2. That would really be the ideal way of expressing this slope, 7 over 2. You could also express it as a decimal of 3.5. So really, your final answer for 16 should either be 7 halves or 3.5. If reducing fractions is a little tricky for you, again, the negatives go away, and you can divide out a 4 from both the numerator and the denominator. The graphing calculator can do this for you. If you just simply press math, enter, enter, it'll give you the 7 halves. You can also just do the division of negative 28 divided by negative 8, and you'll get the 3.5. So anyway, either one of those is acceptable for 16. Last question is 17. George is loading freight into an elevator. He notices that the weight limit for the elevator is 1,000 pounds. He knows that he weighs 210. He's loaded 15 boxes into the elevator. Each box weighs 50 pounds. Identify the rate of change for the situation. There was a lot of information in this problem that turns out to be irrelevant to the answer that we're looking for. Now, in another context, we might need all of this information. However, the directions just simply say, what is the rate of change? So in the context of this problem, the thing that's changing is the number of boxes. So really, all this is saying is, what happens to the total weight as you add a box? Well, each box weighs 50 pounds. What that means is, my rate of change is simply 50 pounds per box. That is the rate of change for this scenario.